Okay, let's talk stress concentrations. So suppose I have a bar here that is loaded axially, and there's a hole in the center of this bar. Well, if I were to and take a slice through here, making a cut as so, and if we look at this section, cross section of this block after we cut at AA, we can see that for the given load condition here of N, we'll have an internal loading. A non-uniform internal loading condition will occur, and on, for example, this upper piece, the condition will look something like this on this side, and then this will be the situation over here too. So we'll have a very unusual distributed load with a higher value towards the hole and a lower value towards the outside surface. Likewise, at the bottom, a mirror image of the situation will exist. So, sketching in here. And here, I'll just put this picture in to represent what I'm trying to say. So we have an unusual distribution of stresses internally due to this hole. Well, in this profile here, the value here is maximum, close to the hole, and it leads to essentially a ×3 stress. So a stress that is 3 times higher than the stress associated with the uniform cross section. If I look at a plot, we can see how the stresses are concentrated based on the size of the hole, twice the radius, divided by the width of the problem. And over here on the y-axis, we have this value K. And K is something we call a stress concentration factor. And it relates the maximum stress over our cross-sectional normal stress, or our average, what we would call in the past our average stress. Of course, we could relate this profile to the normal force with a little bit of calculus. We could take the integral over the area of the stress dA, and so that's a more calculus type relationship to represent what's going on. Now, this sort of simple representation is only good in cases where we are talking below the yield point. So in the elastic range. But it's because of these concentrations that develop that cracks occur. And the crack will first develop at this point and then will propagate down and eventually lead to the failure of the section. This is the sort of thing that happened. It's happened in a number of modern engineering designs, but one of the most famous is this was one of the first jet airlines, and the windows had these rounded corners of the square windows initially as designed. And as they pressurized and unpressurized this plane at altitude, cracks would develop at these rounded corners and eventually lead to failure. And they had a bunch of total losses in this situation, and all due to the concentration of stresses. So to work a problem in with stress concentrations, you would calculate your average stress in the typical section of the material, and then multiply it by whatever you calculate your particular stress concentration is. If we have a hole that we're dealing with in our member, and it has a radius such that when I multiply it by 2 and divide it by the width of the member, I end up with a value of 0.2. Well, I would just cross-reference that on this line, and it looks like I would have a 2.45 stress concentration right here. So 2.45. And you would just multiply your stresses by that value to calculate essentially any situations or effects. If you were designing, that would be your design stress that you would have to correspond to or defer to. So say I put some numbers to this situation, and say I have a 100 Newton load on this member with a hole in the center, and it has a 0.1 by 0.1 cross section. Then I can then calculate an axial stress of 10,000 newtons. Well, my maximum stress that I can expect to see due to stress concentrations would be K times this sigma I calculated above. And for K, I would check out. So this is going to be K times, so I look at my relationship here, and this is just really the stress over the cross section of the top and the bottom portion of this hole. So we're talking the N divided by the height of W minus twice the radius, so the diameter of the hole, and multiplying that by the thickness. And let's say our hole is 0.25 meters in radius. So we end up with this relationship then. And then putting in a value for K. And let's change our hole radius to 0.025 so we fit on this chart. And then we get 2R over W equals 0.05 divided by 0.1, which is 0.5, which puts us right here at 2.15 as our K value. So 2.15. Let's substitute that K in there and solve our relationship for our maximum stress concentration. And we end up with sigma max equals. So in this reduced cross-section, the cross-section that I have outlined in red here, our average stress goes up by factor 2 essentially from our normal stress in the 1 by 0.1 by 0.1 cross section of 10,000 above, which we would expect because it is a reduced amount of material. But in addition to that, there is a stress concentration due to this very unusual distributed load, and the maximum value here ends up being, when we go and check out our K value here of 2.15, based on the size of our hole and the thickness, again, of our member, we end up with then this stress level due to the concentration. Now again, this chart is only good through the elastic range, so have to ensure that that is the case. So in other words, this chart doesn't take into account any plastic deformation occurring.